Good morning, pre-cal students. Um, we're kind of in the thick of the trigonometry, and what I want to do today is to go ahead and give you the inverse trig functions for the other two that I left out, even though they're not very important. You may see them, and I don't want you to feel like they've been left out. And then we want to talk about a couple of types of computations that we can do with inverse trig functions to get you more comfortable with the idea of this new object. And then after that, we'll discuss some new elements of the unit circle having to do with degree measure and arc length and even sector area. So we're still gonna be focused on the unit circle, but we're gonna look at some ideas that actually bring into light other mathematical characteristics of the unit circle that we may not have thought about, or maybe we knew about, but we thought, well, are we going to use these in a trig course? And so, of course, the answer is yes. So let me go ahead and share my screen. I went ahead and started writing up the one for the inverse cotangent, just like we did before. And of course, I lost track of time. So, isn't that good when you're doing math to lose track of time? That maybe might mean that you like what you're doing. So when you look at this particular example, what I wanted to do was just basically describe the inverse cotangent like we did the inverse tangent. And it's fairly universal with the inverse cotangent to restrict the x to the principal branch like we defined last class. So when we look at this principal branch here, x runs from 0 to pi, and remember, these are just the vertical asymptotes. And so when you do this, this is exactly what we've done before, and we'll do the same for the inverse cosecant. Notice again, even though we don't have the calculus, we have what is a decreasing branch. And because it's decreasing, and we've restricted to this particular set of x values in this interval here, we have a one-to-one function. And like I said before, the definition of the inverse cotangent is actually universal. There's no slip up on this. So what we do is like we did before. I've tried to make this look just like what I've done before. Define the inverse cotangent. And so again, what we'll do is we'll say that y equals the inverse cotangent of x as long as x lives between 0 and pi. So now what we're going to do is we're going to flip the range in the domain like we do in any inverse function. Now, again, just remember, every time we do this, we can always take cotangent of each side. We can say cotangent of y equals x, like we're doing in the inverse equation. So this is like doing the logarithm and exponents. We can apply cotangent to both sides and get cotangent of y equals x, and here the cotangent and inverse cotangent would absorb each other because they're inverses. So you can write these too. This is going to be something that we'll often do. I haven't stressed it a lot right now because I'm writing these equations here, which basically tell you the same thing. But I just want you to be flexible like we were with the logarithms. They say logarithms and they say exponentials. And then of course, the inverse equations say, okay, if you compose the function with its inverse, you should get the identity as long as you obey the particular parameters here. So for instance, when we look at this, the cotangent of the inverse cotangent of x will always be x if x lives between 0 and pi. And again, when you look at the second one, you're thinking this will be true, and this is very flexible because the range of the function here, for instance, when we think about flipping everything, the range of the cotangent function is all reals. So when we flip it, we see that now when we put this on the inside, we have to be able to say, okay, well, what's the deal here? For instance, when we look at this, and the reason I'm getting a little bit tongue-tied is that these need to flip. And let me show you why. Maybe you're not up to this point yet. Notice here, we have to respect the fact that we have the domain of the inverse cotangent, which is all reals. So all reals. And then, of course, here we have to respect the range, which will be 0 to pi. The math always self-corrects itself. So again, remember, the range here, which is all reals, becomes the domain of the inverse, and the domain here becomes the range. So again, when we substitute a value of x into the inverse cotangent, it can be any real number, so this must be respected. And then, of course, when we're thinking of the range of the inverse cotangent, it must lie between 0 and pi. And the reason I'm focusing more on this, ladies and gentlemen, is that this x value can wander around. I mean, for instance, a lot of students say, well, you know, when we do cotangent, as long as we don't hit a vertical asymptote, this x could run around the place. And that's true, because, and then you're thinking, I would have to be very careful if I wrote x here to make sure that it was in between these two real numbers, 0 and pi. So that's what I'm going to talk about today. This particular order here has to be defined correctly, because again, the inverse cotangent is only defined, well, in this case, we don't have to worry, it's defined for all real numbers, but this will have to be defined. We know cotangent of x is defined for many, many real numbers in the sense that it spreads across the entire real line also. And so we'll have to, again, look at some instances where we can have flexibility here. Now, the equations here, you're going to think, well, why did you bother to tell us about this? Because this looks like a nightmare. The inverse cotangent of the negative arguments is not as simple. For instance, it's like the inverse cosine. It's not odd, it's not even. We have inverse cotangent of the negative x is pi minus inverse cotangent of x. So that's like the inverse cosine, and also like the inverse secant. And then for the reciprocal, let me write this out, reciprocal rules, just like we had one for the inverse secant, they're not very user-friendly. That is, the inverse cotangent of x will be the inverse tangent of 1 over x as long as x is positive. So we're on this side here. But if we want to apply the inverse cotangent of x to use the inverse tangent, we have to add pi because of the shifting. So when x is less than 0, we have this identity. Again, we probably won't be using this very much just because it's not something we use a lot in calculus. But I did want to make you aware of this because you don't have inverse cotangent buttons on your Google calculator. You have to use these inverse equations. So this is kind of extra because we really won't focus a lot on this in calculus, but I didn't want you to think Professor Ron just forgot this. So now when you draw the graph of the inverse cotangent, you respect the fact that all x's are applicable for the domain, but then you have the range here that exists between 0 and pi. And then of course you think of the reflection in the line y equal x to give you again a nice decreasing curve. Decreasing, decreasing. Again, you don't ever have to worry about confounding anything. If you write something down on a card, you just match it up with the branch that you're using, and then all of this will make sense. If something is switched, then you'll clearly know the indication of that. And let me show you, I've got some from what we did last time to make a comparison. I keep all of the notes that I make in class. Maybe that's a bad thing. So here, when we did the the inverse tangent, let's just compare the two. See, we have the same thing pretty much. The tangent of the inverse tangent equals x. Again, the domains are the same, but now remember here for the inverse tangent, the range is between negative pi over 2 and pi over 2, and here it's 0 and pi. So notice here, screen always freezes. Good old Xfinity early in the morning. Remember, for the inverse tangent, we had the increasing function, so the inverse function also increases. But remember that the negative argument here is very nice because the inverse tangent is an odd function, okay? So this is much more user-friendly. So I want you to make your note cards like Professor Ron makes his lecture notes. And again, when you compare the two, you see this has a little bit more complication, but we really focus more on this. The beauty of this, ladies and gentlemen, is that the derivative of the inverse cotangent is actually the additive inverse of the derivative of the inverse tangent. And that's why the calculus pretty much gets squeezed down because of those relationships. Now, so again, I keep these stacks of papers so that when I have students come to conference hours, I'll say, okay, remember what we did in lecture, so I don't have to actually pull up the video, which would take forever. Now, before we do some computations, I want to go ahead and do the inverse cosecant. Now, let's just remember what that is. That is, let me just entitle this inverse cosecant. We want to spell that correctly. Inverse cosecant. Now, this will be y equals cosecant x. And before I kind of let the cat out of the bag, let's just go ahead and draw a restricted version of it. Now remember, the cosecant is 1 over sine. So we're going to have, just remember what this looks like. And so we're going to have vertical asymptotes at 0 and pi and negative pi and things like that. So let's go ahead and draw a little bit of it. So this is the x equals 0, the y-axis, and x equal pi. And then we can go over here to negative pi, just replicate. And of course, negative pi over 2. And we can mark off the 1 and the negative 1. Now what we remember at pi over 2, we have the 1, right? Sine is 1. So we can go ahead and draw this piece. And then at negative pi over 2, sine is negative 1. And we have this piece. So that's the restriction right there. So you're thinking, well, we could keep going this way and keep going this way. But what has been chosen, at least what Professor Ron will choose for this, will be these particular branches. And notice decreasing, decreasing, but 1 to 1. So we'll say y equal cosecant x restricted. And it's 1 to 1. Again, the calculus will verify this, but we have a nice 1 to 1 function. And so this is how we will build the inverse function. So over here, I can say, well, here we go again, leave out the 0. So we say x lives between negative, well, in this case, we can use a bracket, just like the secant, negative pi over 2 to 0 union 0 to pi over 2. Remember, with the secant, we went from 0 to pi over 2, leave out pi over 2 and pi over 2 to pi. So again, this one's similar, but now you're thinking, look how nice we got this symmetry with respect to the origin. So this function's going to have a lot nicer characteristics, easier to work with. So now we define the inverse cosecant. Now, when we think about all of this and we think about what we're doing, we'll say, okay, y equals the inverse cosecant. And then, of course, now we're thinking that now the domain of the inverse is the range of the cosecant. And so that's going to run from what? Negative infinity to -1 and 1 to infinity, just like the secant. So we'll say x lives here. Again, this just gives you some extra practice, even though we don't spend a lot of time with these. Now, of course, remember, you can write this as x greater than or equal to 1 as a disjunction if you prefer, just as a more compact notation. And then, of course, like I wrote before, remember, this means, I'll just go ahead and throw this in. This just means cosecant of y equals x. They're interchangeable. So now, number one, the cosecant of the inverse cosecant of x equals x as long as we respect the domain, that is x if and only if. You can do if and only if or a comma. They're all really if and only if, but I've been writing them this way. Negative infinity to -1, union 1 to infinity, and then 2, inverse cosecant of cosecant of x will be x as long as we respect the output. And now we see that it's gonna be right here between negative pi over 2 and pi over 2. So we get a lot of practice with symbolic computation and symbolic notation. So you're like, okay, this is a lot, Professor Ron, this makes me feel a lot better, because this, when I draw this graph, it's going to have a nice symmetric orientation about the origin. And so now the negative angle is my friend. It's a nice odd function. I mean, we don't have to, beat ourselves to death with everything we do. I've put so much emphasis on even and odd. By now, you should be very comfortable with those notions. I had a colleague one time say that, oh, we need to not teach even and odd in college algebra because it's unimportant. And I just said, you clearly don't mean that. And he looked at me puzzled. I said, let's move on and forget what you just said. I meant no disrespect. I think he had gotten desperate, thinking we've got to cut down the amount of material in the class. I said, well, if you're going to trim something, don't trim that. So you can see now, even and odd is really what rules the world of the trigonometric functions. We would be really remiss not to have any knowledge of them from a previous course. So now the other nice thing, and I've written here, I put a little happy face with it, is that the reciprocal rule is beautiful, just like the inverse secant, easy to use. So this will be the inverse sine of 1 over x. So the reciprocal rule, the way that the function deals with the negative argument is easy because it's odd, and the reciprocal rule is nice and usable, okay? So you don't have the inverse cosecant key on your computer, on your Google calculator. And so maybe you might be in a physics class, or you may, maybe you'll just avoid these functions altogether. We just don't emphasize them that much, but I don't want you to think that Professor Ron just threw them out. We can now use them. And if you see them in your work, you know that they exist and you have some information about them, which is exactly like what we've done with the others. And so now when we draw this, we get a nice, really symmetric function. So again, we have the asymptote, the vertical asymptote x equals 0 now becomes the x-axis. How funny. So now we have y equals 0, or the x-axis is the horizontal asymptote. And then we can mark off pi over 2 and negative pi over 2. And of course here we've got the negative pi over 2, negative 1, so we have negative 1, negative pi over 2. So we decrease to the vertical tangent. And then over here, we've got pi over 2, 1, so we get 1 pi over 2. And we decrease. Of course, we form a vertical tangent right here, but then decrease and approach the horizontal asymptote here. So this is y equal cosecant of x. A very beautiful function, very nice and symmetric with respect to the origin. So again, I start when I got up this morning and I thought, you know, I'd tell them these functions aren't that important. Well, you know, you do see them, and they're just not the focus in the calculus sequence, but it doesn't mean that you'll never interact with them. And so I want you to be familiar, but notice the emphasis in this class will be the inverse sine, inverse tangent, inverse cosine, and the inverse secant. And these are just like extra to make sure that you have the foundation that you may need if you see these again. So like I say, occasionally it's just nice to know, you know, what if, Professor Ron, what if I saw this and I'm like, okay, I need an approximation, or I've got an inverse sine key, but it's not a nice number on the unit circle. What do I do? Well, you can use these identities here. So just like we have identities with the standard trig functions, we have identities with the inverse trig functions. Okay, so now what I want to do is do a few computations. So you're thinking, how is it that we do all of this? What do we, you know, how do we contend with all of this? What's the deal with computations? So for instance, we know the basic unit circle, and now what we're doing, for instance, if we say, for instance, here's a good example of this. We say that sine of pi over 2, so we're thinking we're inputting a distance along the unit circle. Well, let me make it more interesting than this. Let me stay off the axis. I want to make it a little more interesting, and then I'll do that one. So we have this measurement along the unit circle from 1, 0, a distance of pi over 6. Now we know from our unit circle that where that particular t value, pi over 6, terminates is at the point square root of 3 over 2, 1/2. And so we would say the t value or x value, whatever, corresponds to the terminal point square root 3 over 2, 1/2. And then, of course, last week, Professor Ron said, okay, well, when we define the sine of t, it's the y coordinate of the terminal point. So you're like, how simple is that? Sine of pi over 6 is 1/2. Okay, now, when we think about the inverse function, we think about doing this backwards, but let's just remind ourselves. We say inverse sine of x. So y is inverse sine of x. And what do we know about this? Well, first, we know that x lives between -1 and 1. We have to remember this. And then, of course, the inverse sine of x lives between what? Negative pi over 2 and pi over 2. You just think of the graph. So now we're flipping the range and domain, so to speak. So if you look at this and think backwards, like I say, just say, okay, well, does this make sense? Well, it does, because I know that 1/2 is in the domain of the inverse sine function, and pi over 6 is actually in the range. So I could actually flip this. That is, say, inverse sine of 1/2 equals pi over 6. And so you might be thinking, okay, well, Professor Ron, what if the problem just started like this? It said, what's the inverse sine of 1/2? Well, then you can apply sine to both sides and think of the unit circle. So basically what we're doing is, instead of starting with the measurement along the unit circle and heading to the terminal point, we're starting at the terminal point and going back to the measurement along the unit circle. So we see that this is the reverse path. So if you have values of y from the unit circle, from those terminal points, then you can always easily go to the measurement along the unit circle, as long as you preserve this. So for instance, here's another one. So now you see that we can use the unit circle to evaluate the inverse trig functions basically in the reverse path. So here's another example. What if I said inverse sine of, I don't know, we'll make this make sense. Let's just choose another one. Say we have negative √3 over 2. And you're thinking, oh, okay, Professor Ron, I get you. That's a y value. That's a y value on the unit circle. And then you might be thinking, okay, well, we know that the inverse sine is odd. So the first thing we would do is factor the negative, just because we're lazy. I mean, we want to make it easy. And now, if we cover up this negative, this is a inverse sine of a positive number that's right here, and that's going to remain between 0 and pi over 2, thinking about the graph, how we defined it. And then you think about it, wait a minute, as you move along the unit circle, that moves to the measurement pi over 3. And so this part right here is actually pi over 3, reading the unit circle backwards. But then we apply the negative, so we get the negative of pi over 3. So again, if you look at this and say, well, what's the sine of negative pi over 3? Well, it's the negative of the sine of pi over 3, which is negative √3 over 2. So the key here is that I've shown you how to deal with the negative arguments, but what we have to make sure is that when we actually do these problems, that they're well defined. So when we look here, anything that we would input into the inverse sine would have to live in here, and excuse me, have to live in here. And if it didn't, then it wouldn't make any sense. So for instance, here's another example. Say you had this on WebAssign. I'm just focusing on the inverse sine because it's a good place to start. What if you had inverse sine of -2? Well, then you're thinking, well, if that were equal to maybe x, I would say sine of x equals -2. You're thinking, well, that doesn't make sense. Why? Well, first, -2 is not in the domain of the inverse sine. And if it were, it would say that -2 was in the range of the sine function, which is clearly nonsense. So here we would say undefined. So the fact of the matter is that the inverse trig functions are restrictive as to inputs, whereas the regular sine function takes any real number. Any real number. You can wrap around the unit circle and counterclockwise, clockwise, any positive number, any negative number, whatever. that's a very flexible function. But when it comes to the inverse sine function, there's a lot less flexibility. So if you get to something like this, you go over to your thought process, or you think, oh, well, where's my note card on inverse sine? Oh, don't worry about it. I know it. I'll just write it down. So when you do these problems, just quickly jot down the range and domain of the inverse trig function, and then that covers you. That way you know what you're dealing with. So this wouldn't work. This is undefined. So let's look at another one. Say we want to do maybe, well, we've been doing inverse sine. Let's do an inverse secant. So remember, let's just do this. Y equals inverse secant. Now remember, this had an unusual definition. In this particular case, x is between negative infinity, -1, union 1 to infinity. And then the inverse secant of x lies between 0 and pi if you leave out the pi over 2. Okay? So now we're like, okay, well, this is a fairly straightforward function. And also we have the reciprocal rule. Okay, so you might be thinking, since Professor Ron has given us the reciprocal rule, I could just focus on the cosine, which you probably know a whole lot better because you think of the unit circle and you just think of the x coordinate. So for instance, here's an example. Say we have inverse secant of, let's just say here, 1 over √2. And you're thinking, well, that's √2 over 2. Professor Ron just didn't rationalize it. And then you say, okay, well, I can use the inverse rule, I mean the reciprocal rule, because that's easier for me to work with. So I'll say, okay, well, this will be 1 over, oh, sorry, that we reciprocate the argument. I said reciprocal first. Math is so nice, tells us what to do. So we say we do the reciprocal rule, so we reciprocate the input. So this is inverse cosine of √2. Oh, and I need to flip these around, don't I? Because that's, let me just say something. That was not defined, was it? Because 1 over √2 is not in here. So there we go. That makes sense. Notice, and let me just show you why that was good. √2 lives from 1 to infinity. So what I had originally written was undefined because when I did 1 over, when I did √2, that's too big for the input of the inverse cosine because it's bigger than 1. You see? So again, it self-corrects. So let me give you something that's defined. This is actually defined. I didn't want to start out with undefined. And then we reciprocate. And now we've got something we understand. We have the inverse cosine of 1 over √2. So let's remind ourselves what the inverse cosine looks like. So x lives between -1 and 1, which this clearly does, and the inverse cosine of x lives between 0 and pi. So now we've got, okay, well, we think of our unit circle and we move up pi over 4 radians, and that gives us an x value of 1 over √2. So this is pi over 4. So again, it's backwards. We're just reading, when you think about it, we're just reading the unit circle backwards. So when we say inverse cosine of pi over 4, we're here. I mean, excuse me, of 1 over √2, we're here, and then we move to pi over 4. We go backwards. So this right here is right there. And then we take the backwards path. what's the backwards path? This is 1 over root 2 or root 2 over 2, however you want to write it, to pi over 4, and we get that. But again, we started with the inverse secant, and then this is just the reciprocal rule. So you should already know these, but you probably don't. That's okay. Nobody's ever caught up in my class. That's just the way it is. I demand a lot of my students, and that's okay because it's going to make you brilliant one day. Now, so we think, okay, we got this nice reciprocal rule. Let Professor Ron get a little bit more clever here and throw in some negatives. So here's another example. Say we look at something like this. Say we have inverse secant. And let's think of something that's in here, but in the negative category. So let's flip over a value that we know of the output of the cosine function. So we'll do -2 over root 3. Okay, and of course, -2 over root 3 is less than -1. So this makes sense, being that 2 is bigger than the square root of 3. So this is defined. So if you're going to make up problems, you can just make sure that they're defined. Clearly, the reciprocal rule will always let you know if you start to use it. You see, if I had written the problem the way I did initially, when I started to use the reciprocal rule, I said, well, this is not defined, I'm done. But I didn't want to do that. So I made the change so we could actually work the problem. So now we look at this and say, okay, well, we've got, let me again show you, we can deal with the negative arguments if you want to use the rules I gave you before. So remember, when we defined the inverse secant, I gave you a way to deal with the negative arguments, which will make your life easier. So now if we have the inverse secant of a negative argument, we can actually do this, okay? Or then just pass it along to the inverse cosine, whichever. So we'll just go ahead and use this one. So now the inverse secant of a negative argument will be pi minus inverse secant of 2 over root 3. That gets rid of the negative. And now we have the nice reciprocal rule again for the secant. So this will be pi minus inverse cosine of the reciprocal, root 3 over 2. So if you go ahead and deal with the negative, you don't have to worry about it causing you issues. That's why I went ahead and provided the negative argument here. This will help you, and that way you'll actually get these problems correct as opposed to just guessing at them or using your calculator like you think that's going to help. Again, this is symbolic computation based on our definitions, and it is essential that you understand this. This is important. Otherwise, calculus will every time you get to these, you'll be scratching your head. So now we can work the unit circle backwards. So we think of root 3 over 2 in the first quadrant. That's what, pi over 6. So again, let's go back to the trusty Professor Ron unit circle. So we have root 3 over 2. We go backwards to pi over 6. So this gives us pi minus pi over 6. So that's 6 minus 1, which will give us 5 pi over 6. Which, of course, this makes perfect sense because 5 pi over 6 is in the range of the inverse secant. You see? So the beauty of the inverse trig functions is that we don't really have to learn anything new. We just have to respect their domains and ranges. And so when we do these kinds of problems, do just like what I'm doing here. Get familiar. Just say, okay, well, what did Professor Ron give us to work with? Go ahead and write this down to remind yourself of what you're dealing with, and then just work through it. If you need to work with the negative, here we know we can factor because the inverse sign is odd, but the inverse secant doesn't have that property. We have to say pi minus the inverse secant of the argument without the negative sign. So again, and then we can use the reciprocal rule. So again, the idea here is that we use what we know with a few minor adjustments, keeping in mind what we have here. Now, one more type of computation I want to do has to do with the inverses, the inverse equations. So for instance, here's an example. So say you were asked to do like an inverse equation, for instance. So let me write down a couple here. So we have something like this. Say let's pick on inverse cosine. So remember, y equals inverse cosine of x. We'll just write down what it is. We have in this case, oh excuse me, inverse. Make it the more difficult one, or the new one, so to speak. So x lives between -1 and 1, and the inverse cosine lives between 0 and pi. That's how we constructed it. Again, that you see how the inverse secant works really nicely with this function, because their ranges complement each other in the sense that they are the same, except that the inverse secant throws out the pi over 2. So the nice relationship we have between the inverse cosine and the inverse secant is based on this definition. So now we might be thinking, okay, well, what do the inverse equations look like? Number one, and you'll have to think about this, the inverse cosine, or the cosine of the inverse cosine, will be x, as long as we respect the range. Well, in this case, not the range, the domain. Again, all of this is self-correcting. So we're thinking, how does this make sense? Well, again, think about it. The inputs must be in the domain of the inverse cosine, but they all the actual value of x must be in the range of the cosine, which is this. So that's what tells you whether or not this is correct. So if you write it down and like, well, no, that doesn't make sense, do what I do and correct it. And then 2, inverse cosine of x is going to be x. Again, x must be in the domain of the cosine, which that's any real number, but so that's not going to help us. So we're going to say, oh, it must be in the range of the inverse cosine, which is 0 to pi. So you see that the cosine function's not going to help you here. It's very flexible as far as input. So we have to defer to the inverse cosine. So that's how we work the mathematics. So here's the idea of the what? The composition of the cosine function with its inverse. And then of course we had that really nice thing here, cosine inverse of the negative angle is pi minus cosine inverse of x. That's very useful. So this kind of summarizes everything we know about the inverse cosine. And ladies and gentlemen, this you should practice writing down every day. If you don't, you will not know it. The only way you become a mathematician is that you write mathematics and you use your background to construct correct equations and symbolisms, like I do here. And then you check, is this consistent? Oh, wait a minute, I need to adjust this. It's not consistent. That's how you think mathematically. That's what I'm trying to teach you to do. Otherwise, you just simply memorize and manipulate, and that's not going to get you where you want to go, because you're a future STEM professional, and the critical thinking must be part of your daily routine. So here, try this one. So here's a good example. this is the one that gives us all the issue. So compute the following. So we're going to say inverse cosine of, and you're thinking, well, the cosine, I'll just throw in a negative. The cosine is an even function. So you'll think I'm making a difficult problem here, but it won't be difficult. So we'll say cosine of, let's say here, let's do negative 5 pi over 4. Okay, let's do that. All right, so you look at this and say, okay, can I use this directly? And then you're thinking, no, because negative 5 pi over 4 doesn't live in here. The rules that Professor Ron wrote down says that if I want to be able to put x here, I've got to have an x that lives in here by our definition. So you're like, can't do that. So the first thing we're going to do to make it simple is note that the cosine is an even function, so it absorbs the negative. So let's do the obvious first. So we have cosine of 5 pi over 4. And now we look at this and say, okay, well, where does this live? We're thinking 5 pi over 4. So this is just pi plus pi over 4. This lives in the third quadrant. That lives in the third quadrant. So how could we write this with a reference number that would give us an equivalent value of cosine? Well, remember, in the third quadrant, the cosine is what? It's negative, because the x is negative. And so if we use the reference number, the t bar, and put in the negative, we'll be good. So this will be inverse cosine of cosine. So we're going to have the negative because we need the negative value. And then we'll do the reference number, which will be 5 pi over 4 minus pi. So when you're in the third quadrant, you subtract pi from the t value. And so now we have inverse cosine of the negative cosine of what? Pi over 4. Well, we're almost done. Now we have the inverse cosine of a negative argument. Has a negative in it, so we use this identity. So this will be pi minus inverse cosine of cosine of pi over 4. But now this is easy, because if I go to here and I look right here, pi over 4 lives between 0 and pi. So all of this calculation has shown us that now, boom, we can use 2 legitimately. So now this will be pi minus pi over 4, which is 3 pi over 4. And of course, 3 pi over 4 lives between 0 and pi, and that would be your computation. So this is what I'm talking about. When you do this direction, it's easy because the inverse cosine has to be defined. The cosine is very flexible. It can take any input, any real number. And so you can, this is actually defined. You can compute it, but you can't just say it equals negative 5 pi over 4. That makes no sense because the negative 5 pi over 4 is not in the range. So you use the identities that I've taught you to do this computation. So this will help you negotiate inverse trig functions, especially when you get to calculus, because you'll be like, oh, let me write down my unit circle. Oh, what definition of inverse secant are we using? Okay, oh, I've got the inverse rules. Okay, I can do this. So I've got the reciprocal rule, so I'm good, kind of thing. You have to respect the definitions of the inverse trig functions. So that's really the only thing that's tricky. And another thing too, trigonometry as we see it so far is based on the unit circle. And so we must abide by the unit circle and its properties. And so every time we write something, We think, no, is this consistent with the unit circle? And you can easily check when it's not. Like I say, the art of doing mathematics is not rote memorization. It is understanding of the objects and moving the objects forward in deductive reasoning to get to the finish line. And what's the finish line, ladies and gentlemen? It's the solution. So whether you believe it or not, every time you solve a problem, you are actually doing a proof. We have proven that this equals this. So if you say you don't like theory and you're taking a math class that you enjoy, then that's a falsehood. Every time you solve a problem, you are actually doing a proof. It's just the level of abstraction that will make it more difficult. And this is more abstract than we've been doing, but it's certainly based on basic concepts of the unit circle, which when you think about it, by themselves are very simple. It's the synthesis of all these ideas that make the journey a little bit more complicated. Now, let's talk about some properties of the unit circle that, you know, we're thinking, how can we move this discussion forward, Professor Ron? I think I've gotten as much of the inverse trig functions as I can just stand right now. We'll come back to them, ladies and gentlemen, but for now, enjoy. And so remember, don't shy away from them. Just dig right into it and apply the definitions and apply what you know, and you will find that you know quite a bit. So what we want to do is think about the unit circle. Let's go ahead and draw just a reasonable unit circle. So go ahead, and I just want to make an analogy here. So just go ahead and let's just sketch this the best we can. We'll cheat a little bit, especially when I don't do the marks low enough, so I'll cheat on that. There we go. So that looks more like a Charlie Brown head, more like Professor Ron's head, but that's okay. We'll live with it. So as we've been doing at this point, when we think, and this is 6.1, all the ideas here, we're thinking, for instance, that we have some measurement along the unit circle. From the point 0, 1, excuse me, 1, 0. And this is the measurement T. And then where T terminates, that denotes a particular point on the unit circle. We call that XY, P, point P with coordinates X and Y. And so for now, that's been fine. We'd say cosine of T equals X, and then we say sine of T equals Y by definition. Now what we want to do is introduce another abstraction. It's called an angle. So we're going to start at the origin and construct a segment that connects the origin to the point P. So basically we're drawing another radius of the circle. Right here we have a radius, it's 1, and then we have another radius, it's 1. And so what we're going to do is the abstraction is this. We're going to define the angle as the basic distance in terms of T between these two radii. And so we can just put T here. But normally what we like to do is like we like to get crafty and call T like theta or something, but we now can think of an angle as an actual measurement on the unit circle between two radii where we basically have this drawn in standard position. That is starting at 1, 0 and then moving to a point on the unit circle. So again, we think of the distance along the unit circle as being equivalent to the angle. So now we think, we think, and again, this is S1, this is important. We think of the angle T as a measurement of distance between two radii of the unit circle. And this is an abstraction because it's like, well, where do you measure it? Well, could we measure it here or here or here? I mean, it doesn't really matter. We think of that as an angle. And in order to give it some legitimacy, we connect it with the measurement along the unit circle. So now we can think of an angle T, and we can think of a measurement along the unit circle T, like a T number before, or T value, we just thought of as a measurement of distance along the unit circle. Now we can take that distance and think of it as an abstract angular measurement. That is a measurement between two radii. So again, this is really like a measurement between two radii, but it's a little bit more cogent because we're thinking of distance along the unit circle. So now we think in more abstract terms and define what we call the angle, because when we start working with triangles, we don't have measurement along a unit circle. And so we have to think of the distance between two sides of a triangle as the abstract measure of an angle. And so then we're thinking, all right, well, we won't reinvent ourselves. We'll just simply think of radian measure as an angular measure, just like we think of radian measure as a distance of measure along the unit circle. Now, we want to abstract this idea. I mean, this is fine when we think of this as a unit circle. The measurement here and the measurement here are the same. That is, if we think of this as T or as an angle, it's the same. Now let's just say that we abstract to something completely different. So now we think of an angle of a circle of arbitrary radius. So now let's go, let's consider a circle of arbitrary radius. Arbitrary radius R. And so let's draw another circle. So we're not going to call the new angle by the letter T because it's not going to be the same. So let's draw another circle. So now what we want to do is, again, draw another angle. So we'll just take a point here on the unit circle. We're going to abstract. And now we're just going to call the angular distance by theta. So now we know that when we think of theta, we think of distance along the unit circle in radian measure. But now, in the abstract, we're just going to call this distance along the unit circle. Again, this is R now. It can be anything, not necessarily 1. And now we're going to abstract and call this distance along the unit circle. And it doesn't necessarily have to be in standard position, but I drew it that way. We're going to call this distance S, or arc length. That's what we use in the calculus. And Dr. Stewart uses it in his book. We're going to call this the arc length, the length of the arc subtended by the two radii, just like you did in high school geometry. Wasn't high school geometry fun? That's when you actually felt like a real math student. And so now you're thinking, okay, so if this is 1 here, you're thinking, okay, well, how does the t relate to the actual angle measure in the radius? Here it looks like, if we think of a product or we think of whatever, that's just easy because it is the unit circle. So how could we come up with a way to actually, maybe possibly, just thinking, measure this distance here if we knew the radius, which again now is arbitrary, and this angle measure? Is there a way to think about that? Well, there is, and let me show you. So we'll think in general, I'll just say for a complete path, that is once around the circle, we know S equals 2 pi r. 2 pi r. That's the circumference. That is the circumference. That's just based on the fact that the ratio of the diameter of the circumference to the diameter of any circle is just pi. And so we get the circumference of the circle if we go all the way around, one complete path, so to speak. So we're thinking angle measure of 2 pi corresponds to a measurement arc length of 2 pi r. So we're going to set up a ratio and then say, okay, well, if we just have some arbitrary angle here, theta, what's S going to be? So again, we say 2 pi is to theta as the distance around the complete circle is the distance here. So we set up a proportion. And so now, of course, the 2 pi is absorbed, and we get 1 over r equals theta over S. And then just cross multiply, S equals r theta. So now we see that there is a way to actually describe arc length for arbitrary circles if we define angular measure in the abstract sense, just like we did before. So for instance, this might be pi over 6 or pi over 4 or whatever. But here's the upshot here. Now we have a way of defining length about a circle or on the circle, even if we're not on the unit circle. So what we have to remember here is that when we do this construction, we do this construction with our standard radian measure. So we just note theta measured in radians, pure numbers. So theta must be measured in radians. So you're thinking, well, that's easy enough. So what students like about this is that they're like, oh, I get it now. If r is equal to 1, then S equals theta. That's just saying S equals theta, T equals T. So now the thing is that if we start with the unit circle, we can abstract to a circle of arbitrary radius and get a consistent measure. So again, whatever we get here must work here, and we see that it does. So that's again, the art of doing mathematics. You're thinking, well, how simple is this? That's just general math taking proportions, but it's done in a way that preserves what we already know about the circle, and that specifically the Euclidean circle. Now you might be thinking, well, let's just kill 2 birds with 1 stone. We've got all this work here, and we might as well, this way Professor Ron doesn't have to draw another circle, and you, ladies and gentlemen, don't have to draw another circle. So we'll call this formula 1. All right. Now we've abstracted, And we're thinking, okay, well, while we're at it, can we just think about areas of sectors? And you're thinking, what do you mean by that, Professor Ron? Well, what if, ladies and gentlemen, we thought of just figuring out what the area of this piece of pie is? This is what we call a sector. So you look at that and say, oh, I get it, I get it. So that's part of the area of a circle. So that's another proportion. So we might think of this. So we'll say the area bounded by the circle and two included radii is called a sector. So a sector is like a piece of pie, so to speak. You have the circle and the two radii, which define a piece of the circle. I mean, of course, if you just had one radii and you went all the way around, you'd have the complete area of the circle. So again, we're using some results from Euclidean geometry to move these problems forward. Otherwise, we'd kind of get stuck. So we're thinking if we have this as a sector, so this is what we define as, say, a sector of a circle, sector of a circle. The area bounded by the circle and the two included radii. And sometimes we just get fancy and say circular sector. I don't know. Or just say sector. I don't know what you mean. So again, we set up a proportion. So we're thinking, how do we find the area of the sector? So we'll think, okay, well, we'll do the same thing again. If we go all the way around, if we have a theta that is the entire circle, that is 2 pi, we know from Euclidean geometry, and even you'll be able to prove this in calculus, that the area of the circle is pi r squared. Now we do the same thing we did over here for some arbitrary theta, and we'll just call the area A. So we'll just say let A equal area of sector. And we set up a proportion like we did here, just like we had here. And so now the pi's absorbed, so we get 2 over r squared equals theta over A, and then of course we can just cross multiply. So now A will equal 1/2 r squared theta. Again, where theta is measured in radians. So that's formula 2. Again, very easy to remember. So now we're thinking, okay, just by abstracting, deciding what angle measure means relative to measurement along the circle, and abstracting to a circle of arbitrary radius, we can now define arc length for any circle as the product of r times theta, where r is the radius and theta is the angle measure in radians, pure measure, pi over 6, 2, 3, things like that. And then, of course, if we are interested in the area of the sector, again, the arc length and the radii define an area. That's called a sector. And we're thinking, okay, let's use the area of the entire circle to find a formula for the area of the sector. And we find that easily to be 1/2 r squared theta. Again, where theta is measured in radians. So you're thinking, wow, we've got some nice formulas here, not too difficult to use. Again, the WebAssign gives you really, really nice formulas or nice problems to work on, and you get to use these. But make sure make sure every time you use these formulas that you're using the pure measure. That's essential. Pure measure, just like we started with the pi over 6, 1 radian, 3 pi over 4, things like that. Nothing, no degrees. And I'm going to define what a degree is. That's why I did this first, because, ladies and gentlemen, when we think about other ways of defining measurements of angles, that's what humans created. This is pure measure. This is intrinsic in the universe. What we come up with may not even be that great, but we're used to it. And since we're kind of lazy, we like it. And let's face it, you go up to someone on the street and say, could you mark off an angle of pi over 2 radians? They may look at you, but if you say 90 degrees, they're like, I got it. So, you know, we're kind of used to what we know. So with that said, we've got our formulas for the sector of a circle area. And we have our formula for arc length. Let's go ahead and write a formula for a new way of measuring angles. And you learned about this in general math. Probably before that, you were in the 5th grade, you learned this. So we're thinking, this is called degree measure. Now, there is nothing special about this. There is absolutely nothing special about this, except it stuck. And because it stuck, we use it. It's unfortunate, but it stuck. So what we're going to think of in this particular case is we're going to subdivide the circle into 360 parts, and we're going to call those parts degrees. Again, another abstraction. So divide the circle. Again, it doesn't matter if it's a unit circle or a circle of arbitrary length. The angle is an abstract measure. Divide the circle into 360 pieces. Call these pieces degrees. So we're going to almost think about the degrees. You can think about minutes and seconds and things like that, but that's really old school. I mean, that's older than Professor Ron, so I'm not going to say much about that. So what we're going to think of is that we'll say, okay, so that's going to mean 2 pi radians will correspond to 360. And the normal notation for a degree is a superscript O. It's not really a 0, it's just a little O. Who knows why? It's standard. So when you think of degree, you think of the superscript little 0 here. And then you're thinking, okay, well, 2 will divide the 360 to give us 180. So we're going to see, at least from this, I mean, somebody was at least smart enough to take values, divide the circle into values that were at least user-friendly. So we're going to see that pi radians will be equivalent to 180 degrees. And this will be the conversion factor. So this implies, or equivalently, theta measured in radians will now be pi over 180 times theta measured in degrees, or theta measured in degrees, just solve for theta in degrees, will be 180. I'll leave the degree part off. You can stick it in there, I guess, make it look right. Degrees are still pure measure. Like we say radian, you know, it doesn't make it but the thing is, when you're using the arc length and the sector area, that's based on the pure measure, the pure radian measure, not the degree measure. And so you can't use degree measure when you're using sector area and arc length, because that's not how we derived it. And so we can think of pi theta in radians. So we have these two, just one actually, they're equivalent. We have the conversion factor, so to speak. Now, you don't have to stick the degree in here. We just think of this as a number. So since I'm not writing radians, I'm not going to write the little degree bit, because that would just make you think you have to type that into WebAssign, and you don't. So it's, again, it's pure measure. Like I don't write pi radians. I'm not going to write 180 degrees unless, you know, and for instance, to make things clear, when you're actually given a designation, for instance, someone might say theta equals 45. And if they just say 45, that's 45 radians. But if they do this, you know that's degree measure. So again, we're fine with this, knowing that the theta, or excuse me, the pi corresponds to the pure radian measure, and the 180 corresponds to the degree measure. So we look at these as a conversion factor, so to speak. So in order to make the difference between radian measure and degree measure here, and again, when you think about this, I'll go ahead and get rid of these right now. When you think about this, in order to, again, understand the difference, we'll use a degree measure here, the superscript 0, to denote 45 degrees. And then you can say, oh, well, I need to do an arc length calculation. Then you can say, well, I'll just do my conversion factor into radians. So this will be pi over 180 times 45. And then, of course, if you look at this, 20, 4 times 5 is 20, and 4 times 40 is 160. So this actually, 45 divides 180 4 times, and you get pi over 4. So if you needed to do a calculation with arc length or sector area, and the angle was 45 degrees, you would have to convert it to pi over 4 radians. So I know in order to make this all wash, we will often have to put the degree symbol here, just so you know this is not radians. So someone might say it's 45 and write out the word degrees, but usually, you know, it'll be 45 degrees. We'll like say pi over 4, and the assumption will be radians. So we're a little bit sloppy. We're a little bit sloppy, I agree, because when you see an angle with nothing but the number, you assume radians. But if you've got the little superscript here, you know that it must be a degree measure, because that is the common symbol that we use. So now we think of this as the conversion factor, where we write both of them as pure numbers. Now, excuse me, let's go ahead and get the degree measure for all of the radian measure in the first quadrant, and then cheat to get the rest for the rest of the circle. So we've got one right here. So now, what about when theta equals 0 degrees? This will just be, well, let's just say we've got what, pi over, well, no, we need to, sorry, we need to do this backwards. You're thinking we've got the radian measure. So this was cheating, but I knew what I was doing. So here we'll say theta equals 0 radians. So this will correspond to theta equals 0 degrees, obviously, not going anywhere. Theta equal pi over 6. So we'll do the conversion. Pi over 180. Oh, now I'm doing this backwards, so I need to do 180 over pi, like we had here. And then pi over 6. The pi's absorbed, and 6 into 180 is 30. So we get 30 degrees. So we'll do the 30 degrees to make sure that you don't read this as 30 radians. Pi over 6 radians is equivalent to 30 degrees. Pi over 4 radians is equivalent to 45 degrees. Oh, now your general math is coming back. What about theta? Well, we know what this is. If we do pi over 3, this should be 60, right? Well, let's just verify. So we have 180 over pi over 3. Of course, the pi's absorbed, 3 into 180 is 60. So pi over 3 radians is equivalent to 60 degrees. And then the very last one will just be what? Pi over 2 radians. And we know what that is, and we use it every day. So we have pi over 2. The pi is absorbed, and 2 into 180 is 90 degrees. So we're like, okay, we've got the first quadrant. So let's go ahead and fill in all the degrees. I'll do the circle a little bigger. So now you notice if you look at Professor Ron's unit circle, you see that I added degrees because I had a student that said, would you please put degrees on this circle? So I told you I had to find my code for it, which I thought I had lost, and I found the code and I just input the degree measure. But she said, I really would like degrees on this unit circle. I said, okay, you got it. Well, I said, hopefully you got it. I have to find it. I find my Calculus 2 notes on these websites that sell stuff to you all. So my students are putting my notes on Chegg and Course Hero, which is fine. I think my unit circle's on there too, but I don't care. If it helps you learn, fine. And if it's free for my students because of it, that's fine. Maybe we'll get more students at the North Campus. So when we think about this, we love to make our world efficient. So now we can say, okay, so kind of halfway in between, we'll just do this now 45 degrees. We'll just leave out the radian measure since you already know that. And then we'll do like, so 30, 60. So we got 0 degrees, which is again 360, right? Then we have 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And now let's just go ahead and use the symmetry and mark off the other places here. Right there. So now we'll just do cheap. So here's first quadrant, second quadrant, third quadrant. So we're getting all these nice formulas to do problems. So now we'll just say 90, we'll just, again, plus 30, that's 120. And then we can do 90 plus 45, that'll be 135. And then we can do 90 plus, well, 60, so 60, that'll give us what, 150. And then of course, 90 plus 90 is 180. Now just now add 30 to 180, we get 210. Add 45 to 180, we get 225. Add 60 to 180, we get 240. Not very difficult, huh? The radian measure is much more complicated. That's why you see this is popular and why it has stuck. And then of course, 93 times, that's what, 270. Now add 30, we get 300. And then now here we can add what, 45, that gives us what, 315. Now add 60, that gives us 330. So now you can see here that all of this is the additional markings here, 30, 45, as we 120, 135, 150, 180, 210, 225, 240 as we have here, 270, 300, 315, 330, 360. So the degree measure is really simple. I mean, let's face it, ladies and gentlemen, degrees are simple, and that's why they become so popular. But when we think about the measurement of calculus, we think about pure measure. When it comes to doing computations, we must use the pure measure, the radian measure. You have a little toggle on your Google calculator that says radian degree. So if you're going to use a degree measure, you have to tell your calculator, or you have to use the conversion factor. Okay, so that really is a point of logic. And when it comes to measuring distances in calculus, we measure distances with pure measure, the radian measure, not degree measure. So don't let degrees be a curse for you. Let degrees be useful, because we like to measure triangle angles with degrees, because that's what we're used to. We like 45, 45, 90 triangles. We like 30, 60, 90 triangles. There's nothing wrong with that. But we see that for triangles, the degree measure is actually suitable. But when we talk about the unit circle, not so much. And of course, when we're graphing functions, degrees are horrible. That's not going to work at all. So the idea here is that we can now work with angles being equivalent if they're separated by what multiples of 2 pi. Now, if they're separated by multiples of 360 degrees, they're equivalent, or they're called coterminal. So if you want to generate equivalent angles, we'd always just add a multiple of 2 pi. If you want to generate equivalent angles in degree measure, just add a multiple of 360. That's what we call a coterminal angle. And again, that's trivial. There's some questions like that on WebAssign, but you won't have any issue with those. So when we look at the degree measure, we just say we have an alternative form, and we have this nice conversion factor. And you always know how to do the conversion factors, because the degree here must ascend to the numerator when we convert to degrees. The radian here must ascend to the numerator when we convert to radian. So that'd be an easy way to remember that. Again, so much easier than inverse trig functions. After you do inverse trig functions, you look at this and say, well, yeah, that's why we did that in the 5th grade, and waited on the inverse trig functions. Now, the last thing we want to do is talk about motion along a unit circle, or motion along a circle. So motion along a circle. So we can think again of the theta. Let's just do a little circle here. We have an angle theta. So when we think about a circle, we can just do an arbitrary sector, and we think of an arbitrary angle. And we think of motion along the circle, say like your little ant moving along the circle. So we can think of angular velocity as we use the symbol, or we'll start out with theta divided by some measurement of time t, where t corresponds to time. So we might say that the wheel rotates at maybe pi over 4 radians per second, or something like that. And so that would just be a way of creating circular motion using the abstract concept of angle per unit time. And the letter that we use for this is the Greek omega. This is what we call angular velocity. So that's a new construct, angle measure per unit time. And then we're thinking, okay, what does this imply? Well, then of course we say, well, what if we did the same for motion So we do an angular measure, and say if you're a little ant here and you're moving along the circle, and you want to say that you're covering a certain arc length per unit time. So you take the arc length and divide by the dimension time and say, okay, well, arc length is r over theta. Well, now you see where I'm going. So we just get r times theta over t. So we get r omega. So now we can think of this as a linear velocity. So we'll say this will be v, or nu for linear velocity. So we have angular velocity, and now we have what we call a linear velocity along the circle, linear velocity. I mean, this is so simple, it's truly easy. So the only new symbol is the omega, okay? So we think, all right, well then of course we can think 1 revolution. So 1 revolution would correspond to 2 pi radians. Or we could say 1 revolution. Well, I'm just going to say that because when we're doing measurements, we have to use radian measure. Degrees don't make sense. So 1 revolution will be equivalent to 2 pi radians, things like that. So now we can, again, we can think of an angular measure, and we can think of a linear measure. Say, like I say, you know, back in the day, we had long playing records and phonographs, but we don't have that anymore. You all are kids of the computer. But when I was a kid, we had records. And you know, we used to put stacks of records on the turntable at Christmas and just play Christmas music all the time. And of course, now I had a nephew that picked up the stack after Christmas and threw all the records down the stairs. And I thought, my goodness, you ruined our records. But I said, you know, that's okay. If that brought you joy, I guess we'll just have to live with it. And my mom never told me that that happened until many years afterwards. So I always joke with my nephew, saying, I said, you know, you put those records to their early demise, and he just kind of chuckles about it. But the thing is that the records are getting a resurgence. You can actually find record players on the internet, and people still have their vinyl records. So I certainly honor those individuals who have done that. Now, what I want to do is look at an example using this angular measure. So, for instance, here's an example where we can utilize some of the topics that we've developed in this class. So here we go. And here's an interesting example. So it says in your WebAssign, and there's a nice problem using circle area or circle sector about the cow, the tethered cow, and I gave it a name, Alonzo's tethered cow, from a former honor student that I taught, who actually went into public health. He was going to be an engineer, but now he's in public health and doing very well. But he liked the problem, and so I deemed it Alonzo's tethered cow. So you'll see it when you do your WebAssign. So we have a wheel diameter. Wheel diameter is 20 inches. And we want to compute the distance traveled if the wheel, so compute distance traveled if the wheel revolves 1,000, actually 10,000 times traveled, if the wheel revolves 10,000 times without slipping. So no skidding. So we're not driving in snow or anything like that where we're, you know, just spinning our wheels, so to speak. No spinning wheels. So now you're thinking distance. So, and here's what WebAssign says. Of course, they're going to make your life more difficult. And then they say, oh yeah, they say in miles. So we'll get an exact answer. And then they would like you to give a 2 decimal. If they don't say approximate, you give an exact answer. And I'll remind you, do not give me decimals where it doesn't say approximate. You're going to make Professor Ron mad. So if it doesn't say approximate, you use your pi's, you use every the symbols that I do as I work my mathematics. So 2 decimal approximation. So work it out exactly, and then use your Google calculator if WebAssign asks you to do that. That's always the case, as you well know. So now distance is r theta. So we've got what? We've got a diameter of 20 inches. So the radius is half that. So we have 10 inches. And then we've got 10,000, well, 10,000 times. So we've got 2 pi for every 10,000 revolutions. So we've got an angle of 2 pi. Let's see. And then we have, how do I want to write this? Oh yeah, let me write it this way. Let me write it this way so you'll see the dimensions work. This being a little bit sloppy. So I'm going to use this, but I'm going to write it. Let me write it in a way that's a little bit better. So we have 2 pi radians per revolution that make it a little bit easier to write in the computation. So yeah, do it like that. So now we have 2 pi radians per revolution times 10,000 revolutions. Okay, so the revolutions absorb, and so we have 2 pi radians. So that's a lot of distance, and we have 10 inches. So the issue here is that this is pure right now, but inches are not miles, so we can convert to miles. So first we'll say 12 inches in 1 foot. And then of course you all learned this back in general math. They're 5,280 feet in a mile. How funny. Never thought we'd be doing this. Yeah, when you get to Cal 2 and you start doing this dimensional analysis with applications of the definite integral, you think you're going to be back in general math, and it will make you crazy. So now we see that the feet absorb, the inches absorb, and we're left with miles. So let's go ahead and reduce this. So notice we can do some simple reduction right early off. Notice here that we've got a 10 here and a 10 here, so that absorbs that. So we'll have 2 pi times 10,000. And then of course we have the 12 times 528. So again, the 10 absorbs that 10 to leave us with 528. And then we have the 2 pi times the 10,000, and then of course the 12 downstairs with the 528. So let's just keep going. So again, we can get rid of a 6 or a 2 out of here. So this will be a pi, and this will give us a 6 here. So divide by 2, pi over 6. And then here, let's see what we have. We've got a 4 here. Yeah, we've got a 4 in this. So that would be a 1, and then a 12. So that would be a 3, a 132, and then a 4 in here. That's going to be what, 2,500? So when we divide, in this particular case, 10,000 by 4, we get a 2,500. And so now let's just keep going. So let's see, we've got another 2 here, or let's divide by 2. So we've got a pi over 3. And then we've got a 1, a 2, 5, 0, 132. So of course that 3 doesn't go anywhere. So here, let's see, we've got another 2, so pi over 3. And so here with a 2, that gives us, let's see, a 6 and a 6, right? 66. So 2 into 13 is 12. I mean, we'll go 2 into 13 will go 6 times, and then a 12 another 6 times. and then 2 here. So that'll be a 6, a 2, and a 5, 625. And let's see, what does that give us? So that's 25 times 25, and that doesn't, so we're done there. So that'll, no more common divisors. So we have 625 pi, and then that gives us an 18 and a 198 miles. Or, well, let's just do MI to abbreviate since we're going to be lazy, MI. And now let's go to our Google calculator and see what we get as an approximation. Now, let me find it here. Let's see here. So let me go and find my Google calculator. So Google Scientific. And let me get rid of this. Too much stuff in here. So move that down. Oh, I don't want that. So let's see here. Share. Here we go. Okay. So here's our Google calculator. So we're going to have 625 times pi divided by 198. And this will give us 9.9166. 9.9166, which we can round to 2 decimals, or 9.92 miles. I certainly prefer the exact, you know, and that's okay. But when we do our calculation, I mean, if WebAssign just said, okay, stop, and no approximation, here's your answer right here. But then maybe you've got a client that needs an approximation, so you use your Google calculator. So that's a lot of distance. If a wheel of 20-inch diameter revolves 10,000 times, you travel 9.92 miles, as long as you don't slip. I mean, let's just say we're not in the rain or in the snow. Now, there's another example here that's of similar nature that I want to just say a little bit about. So this is just using the basic ideas of circular motion. So here's another example. So we have a car wheel of radius 13 inches, has radius 13 inches, and then it says rotating 800 revolutions per minute. That's called RPM. All of you individuals that work with cars and stuff, you probably see RPM. And then it says compute. These are just arithmetic problems. Compute the speed in miles per hour. And remember, we know that speed, and then of course over here, notice we got this nice formula. V is R omega. So we remind ourselves R omega. So we can do it. So V, so that's going to be and then of course, you know, miles per hour. Here we go again, 5,280 feet. So we have 13 inches. And then we have 800 revolutions per minute. That's the angular measure. Now, just to make, well, that's how we do in revolutions. But remember, right here, 2 pi radians per revolution. So let's go ahead and convert that. 2 pi radians per revolution. That's a better way to write it so that you go ahead and get the right units. So we've got everything here. This is our R omega. So this is truly omega now, where we have radians per unit time. But now we need to convert inches to miles, and we need to convert minutes to hours. So we'll have 12 inches 1 foot, 5,280 feet, 1 mile. Till I ran this morning, my nose is itching, but I feel so much better. I felt lousy the first part of the week, but you know, it's all good. Drink plenty of water. And then we have what? Minutes. So we have what? 60 minutes, 1 hour. So when you do the conversion, again, now we notice that the minutes are converted to hours. So we have the per hour. The revolutions are converted to radian measure. And then the feet are converted to miles, the inches to feet, and then the feet to miles. And so we got miles per hour. So now let's get all the numbers. We got the radian, we got all the stuff good, so you can leave out all the units because we managed to get that correct. So let's just write it down. So we've got 13,800, 2 pi, just run on down, 60. And then downstairs we have 12 times 5,280. So now, like we did before, let's just go ahead and get rid of some 10s. So we can get rid of the 10 here. So well, let me just go ahead and write this first. So we've got 13, that's prime. And then here we've got a 4, so that'll give us a 200. So divide by 4, that gives us a 3. So divide 12 by 4 gives us a 3. Divide 800 by 4, that gives us a 200. And now here we've got a 2 pi, and we can divide by 10. So that'll be 528 times a 6. So again, divide 5,280 by 10 to get 528. Divide 60 by 10 to give us a 6. And now we can get rid of the 6 there with the 3. So we got, let's see, let's go ahead and divide by 4. We know we can do that. So 13. The 3 is gone, and that will check that off. That's going to leave us a 2. So this is checked. And then we can divide by 4 here. That's going to give us a 50. And then division by 4 here, that's going to be a 1 and a 3 and a 2. And then of course we have the 2 pi. So we've got this, and then the 2 pi. So now let's see what we get. We can go ahead and keep dividing. We can do a 4 here. So this will be a 13. And then let's go ahead and divide it out of here. We've got a 2, and then divide this by 2. That gives us a 25, and then a pi. So divide this by 4. So that's going to be a 3 and another 12, a 33. So let's see, 3 times 11, and there are no 3s in here, no 11s. So this will be 13 times, oh, let's do it this way. So we have 10 plus 3 times 25 pi over 33. So that's going to be 2, let's see here, 2, 13. Let's see, did I drop I've got my 5 here, 25. So let's check here. So that's going to be a 13. And I've got, let's see here, 13. That looks good. We got a 2. And then we've got, do I have too many 5s? Just a second. It looks like it's kind of big here. So let's see, 3, 50. Let's see, that'll be 250. So that's going to be, let's check here. I think I've dropped a number somewhere. Let me just look back through here and find it. So we got a 13, we got a 200, a 3, and so we dissolve that. That gives us a 2. We've got a 2 pi, and then we've got the 50 here when we divide by 4. and we divide this by 4, we get a 1, and then we get a 3 and a 2. That looks good. And then here, let's see, we divide by 4. So I've got the 2. Okay, 4, so that's going to be a 2 here, which gives us a 25. And then a 2 here that gives us a pi. And then we got a 33. And then, oh, I see what I did. Sorry, forgive me. So do this way. Do this, just go ahead and write this 13 times a 50 times a pi. That's a better way to write it, which is called correct. And so that'll be a 5 times a 3, which is a 15, 65. Yeah, that looks better. No, when I broke down this, I didn't write my arithmetic correctly. So that looks good. That looks better. And so now let's see, WebAssign says no approximation. So this will be in miles per hour. And I kind of like this better anyway. So what we see here is this is just like the last problem, except in the last problem, we just get miles because we're just computing a distance, and then WebAssign asks for a 2 decimal approximation. And then here, we're asked to find a linear speed in miles per hour. And so we use our linear speed as r omega, and then we just do the dimensional analysis like we're in chemistry class. And then you can reduce these. But of course, what I'm doing here is symbolic calculation to where we basically reduce all of the common factors until now. Notice this is 3 times 11. That's a prime number, that's a prime number, and that's just 5 squared. And so this is completely reduced, and then we get our exact response. So WebAssign wants that. So I actually prefer this, and there are times when the approximations do make the problem easier, because I'm sure you don't do this in your calculations. But just remember, when you're in physics and when you're in engineering classes and they want an exact answer, this kind of computation will be useful. So now what's left? What we'll do next is we will, now that we've talked about the unit circle and degrees, we're now going to forge into imposing triangles on the unit circle and see how that impacts our definition of the trig functions using the unit circle. But you see, it's going to be very simple when we impose the triangles. The x's and the y's will just become legs of right triangles. So the beauty of the right triangle approach will complement the beauty of the unit circle approach. And then, of course, with this new abstract measure of angle, we'll have a nicer way of describing triangles, which will be more in line with what you did in your previous classes. Okay, well, Professor Ron is done today, and hopefully this was a little bit easier than the inverse trig functions. The inverse trig functions will require that you put those items on a note card and commit them to memory through understanding. Okay, that's the main thing. But I think that you're going to enjoy this, because when you get to calculus and you see inverse trig functions in calculus 2, you won't shriek at them. You'll say, oh, I know what to do. Let's just learn the calculus. So thanks for your attendance today, ladies and gentlemen. I hope everybody's doing better. I know I feel better now that the week is ensued. If I can get up and run in the morning, then I have energy. So I'm thankful for that. Always thankful for blessings. So you all continue to work hard. If I don't see you at the conference hours, I'll see you next week. Everybody take care. Thank you.
Have a good day, sir.
You too.
Thank you.
Bye, everyone.
See you.
Have a good day, everybody.